Bismillahirrahmanirrahim. Hello students, welcome to the Electrical Engineering channel. Today's lecture is based on regression analysis. Regression analysis gives information on the relationship between a response variable and one or more independent variables to the extent that information is contained in the data. Improperly compiled data results in poor fits and conclusions. So basically, the purpose of performing the regression analysis is to find the best mathematical function which matches the experimental data. For example, in this plot, you can see that these are the experimental data points, and we have to find out a mathematical function that best fits this experimental data. And after evaluating that mathematical function, we can plot that mathematical function. And by looking at the plot, we can analyze or we can examine the suitability of that mathematical model. So in this figure, you can see that the mathematical model or the regression model is actually passing through all of the data points, and this is the best mathematical function that can be approximated using this experimental data. So it means the regression that has been performed is suitable or acceptable. So this is what we have to perform in regression analysis. So now let's discuss the types of regression. First type is called a linear regression. Second type is called a non-linear regression. In linear regression, the response to n data points, for example, x1, y1, x2, y2, up to x and y, and these are n data points, is predicted by a regression model given by. So this is the regression model of linear regression type, and y is equal to a naught plus a1x. So this is the first order polynomial, or we can say that this is the equation of a line. So this is a linear regression model, and a measure of goodness of it, that is how well a naught plus a1x predicts the response variable y, is the magnitude of the residual epsilon I at each of the n data points. So this the residue is actually the error between the value of the mathematical model at that point and minus the value obtained from the experimental data. So this is actually the error. So yi minus a naught plus a1 xi. So yi is actually the experimental value at the point I, and a naught plus a1 xi is the value that has been obtained by the mathematical model. So this is the regression model. This is the experimental data. So this is how we can evaluate the error, and in order to evaluate the best regression model, this error should be minimum. So by finding the minima of this residue, we have to calculate the values of these two coefficients, a naught plus a1. So the best values of a naught and a1 will give us the minimum error between the regression model and the experimental data, and then we will plot our regression model on top of the experimental data to evaluate its accuracy. So first method is to calculate the error between the experimental data and the mathematical model, and then we have to apply least squares method. So we have to take the square of this residue, and the least square method is actually adopted to minimize the error or residual where the estimates of the constants of the model are chosen such that the sum of the squared residuals is minimized. Now, the reason behind evaluating the square of this residue is that if we don't take the square of these residues, then we may get wrong or improper results. For example, if we are just taking the error by taking the difference between the regression model and the experimental data, then in this figure you can see that at this point our error will be negative because experimental value is less than the mathematical model, and at this point our experimental value is higher than the mathematical model. So if we add just the errors at the 2 points and we don't scare them, then we will get zero error by adding only the result for these two first points, because the error here is negative, error here is positive, And if the error here is -1, here the error is +1, and if we just add the errors, we will get zero error. But practically we can see that neither at this point the error is zero, and neither at this point the error is equal to zero. So error exists for both these points. But if we take the squares of the errors, then it will always be positive, either at this point or this point. So that is the reason behind taking the square of the error, and then minimizing that square of the error. So least square error method is applied over here, and after taking the squares of these errors, we have to find out the minima of this method of this error function or residual function. And the evaluation of the minima is just by taking the derivative and equating that derivative equal to zero, and then finding the value of these two coefficients a naught and a1. So this is going to be very interesting discussion, and now I will show you how to calculate the minima and how to evaluate these two coefficients a naught and a1. And after that I will move towards this first example. So let's start the derivation. So here you can see that are the least square errors, and we have to calculate the sum of the squares of the errors for all the n points. So this is the summation, and ei is equal to yi minus a naught minus a1 xi, and we have to take its square. So to find a naught and a1, we minimize SR with respect to a naught and a1. So first evaluate its partial derivative with respect to a naught, and then evaluate its partial derivative with respect to a1. So these are the value equations for the partial derivatives, and we can do the simplification of these two equations, and this 2 can be taken to the right hand side, and here these 2 can also be taken to the right hand side, and then putting this summation term with the individual term in the brackets. So this is the simplified term, and here summation I is equal to 1 to n a naught is equal to n times a naught, and because this term is equal to n, if we add a naught n times, then we will get n times a naught. And here we have two equations. So this is the first equation after the simplification and rearrangement, and this is the second equation after simplification and rearrangement of this equation. Now we have two equations and we have two unknowns. First unknown is a naught, second unknown is a1, and we can solve these two equations simultaneously, and we can evaluate the values of a naught and a1. So from the second equation, a naught is equal to this expression. So this can be taken to the right hand side, and it will be minus a1 summation I is equal to 1 to n xi square. And now we have to divide this term by this whole expression. So this is our a naught, and we can substitute this value of a naught in this first equation. So the first equation will become this term, right? So this is n a naught actually, right? N a naught plus a1 times this summation is equal to this summation. So these terms will remain the same. This is n a naught, and here we can multiply the whole expression with summation I is equal to 1 to n xi, and then it will become this expression. This will become a1 summation I is equal to 1 to n xi whole square, and this will become summation I is equal to 1 to n yi, and summation I is equal to 1 to n xi. From here, we can collect all the terms containing a1 in them, and all the terms without a1 can be taken to the right hand side, and a1 can be written as these two summations divided by these two summations. So this is our a1, and now we have to calculate a naught. But before calculating a naught, we must do some substitutions. Suppose we have introduced a new variable x bar, and this x bar is equal to summation I is equal to 1 to n xi divided by n. So this term will be equal to n times x bar. So if I move this n towards the left hand side, this summation will become n times x bar. Similarly, this summation will become n times y bar. Similarly, this term will be equal to n times x bar, and this term will be the same, right? And this term will also be the same. So this term will become n into this summation minus n square x bar y bar divided by n times this summation minus n square x bar square, n square x bar square over here. So we can take n as common in the numerator as well as in the denominator, and here we will get summation I is equal to 1 to n x I y I minus n times x bar y bar divided by this summation minus n times x bar square. So let's equate this numerator term as sxy and the denominator term as xx as sxx. So this a1 will be equal to sxy divided by sxx, right? So this is the numerator term, and it is equal to this summation minus n times x bar y bar, and this is the denominator term, and it is equal to this summation minus n times x1 bar square. So a1 will be equal to sxy divided by sxx, right? And now we can substitute this term, this value of a1 into the first equation. So this is our first equation, and from here we can calculate the value of a naught, right? So this term will be equal to n times y bar. This term is equal to n times x bar, and we know the value of a1, and this is n times a naught. So all the terms in the left hand side and the right hand side contain n, so we can divide the whole equation by n, so it will become a naught plus a1 into x bar equal to y bar, right? So it means a naught is equal to y bar minus a1 x bar. So this is very simple method of evaluating these two coefficients a naught and a1. And now we are moving towards solving um, the first example on a linear regression, right? So let's move towards this first example. And in this example, we are given a torque needed to turn the torsional spring of a mouse trap through an angle theta is given by. So these are the values of theta, these are the values of t. So theta is our independent variable, torque is our dependent variable, and t is equal to k1 plus k2. This is our linear regression model. We have to evaluate the values of k1 and k2. And just remember that in the previous derivation, here we had a naught and here we had a1, but now we have k1 over here and k2 over here. So the same expressions will be applied again over here, and the expression for calculating k2, previously it was a1, it is equal to this equation. So in this equation you can see that we have four summations. So this is first summation in which theta and t values are multiplied. This is the summation of theta I, this is the summation of torque, this is the summation of theta square, and again this is the summation of theta I. So let's evaluate all these four summations, and then we will be able to calculate K2, right? So these are our theta values, and these are our torque values. So this is the summation of theta by adding all these entries. This is the summation of torque, and these are all the theta square values. Just take the square of all these entries, and this is the summation of theta square. And similarly, these are the values of theta multiplied by t, and this is the summation of theta multiplied by t. And now just put all these summations in this expression. N is equal to 5 because we have total 5 values given in the table. So let's put the summation of theta and t over here, put the summation of theta over here, put the summation of t over here, put the summation of theta square over here, put the summation of theta and take the square of that over here, and then we will be able to calculate K2 as 9.6091 into 10 to minus 2. Similarly, this is T bar, right? So T bar is equal to summation of T divided by N. This is theta bar, and it is equal to summation of theta divided by N. And these summations are already evaluated, and theta bar and T bar can be calculated. Now K1 is equal to T bar minus K2 theta bar. So all values are given. So it is very easy to evaluate the values of K1 and K2. So we can also check the uh, suitability of this model on top of the experimental data. So in this manual, you can see the derivation again, and this is the same set of equations which have been used to evaluate a naught and a1, and these values can be calculated using the MATLAB script. So this is actually the MATLAB script, and by using this script, we can calculate the values of A1 and A0, and we can plot our linear regression model on top of the experimental data and check the suitability of this model. So this is the code, and these are again the same values of theta and t, and this is our x1, right? This is equal to n is equal to length of y. So if we have five values, then n will be equal to 5. This is a1, this is x bar, this is y bar, this is a naught. Again, the same values and expressions are used in this MATLAB code. So this is our y1, and this is our x1, right? This is our n1, and this is our n, and this is our a1. This is y bar, this is x bar, this is a naught, this is y1, and this. Here we will actually plot this code. And so now I am running this code and check the result. Right. So actually this command n is equal to length of y is typed two times. So I have removed first of them. Now I am running this code. So here you can see that these are our calculated values of a0 and a1 for this data set. And this is our regression model, and these are our experimental data points. And from this figure, you can see that this is the best model that actually fits this experimental data. Now I am changing my points. So suppose we have different set of experimental data, then I have to comment these two rows, and I have to uncomment these two rows. So this is our another set of data, and this data is actually given over here. This was my first data set. This is my second data set, x and y, and now I am using this data set to calculate the regression coefficients. So these are our coefficients a0 and a1, and you can see their values, and this is our plot of the regression model on top of the experimental data. So in both the examples, we have seen that an acceptable plot has been obtained between the experimental data and the regression model, and this is a good correlation, and we can see that this regression model is actually suitable. So that is all about our today's lecture. Hope you have understood and enjoyed the content of this lecture. For watching more lectures, please subscribe this channel. Until the next lecture is goodbye.